Okay, angular and tangential variables. The purpose of this section is to be able to relate things that are happening in an angular way to actual velocities in meters per second, as well as accelerations. There's just one concept in this section, and it's this one. We want to relate the tangential speed, the tangential acceleration, and the centripetal acceleration to the angular speed and the angular acceleration. So that's a big mouthful. Some of these words you've seen before. The centripetal acceleration is v squared over r. You've seen that before. We studied it in chapter 5. The centripetal acceleration is the inward pointing acceleration when you're going around a circle, and it's equal to v squared over r, where v is the speed as you're going around that circle. In this chapter, we use v sub t to represent that v here. But it's nothing more or less than just the speed that you're going around the circle, 2 pi r over the period of the circle. But in this case, it's denoted with the lowercase t. So that's all there is to that one. But this speed depends on the distance from the axis. And this is an important new point here. The angular speed that all of these skaters go through is the same. They all rotate through the same angle. But are they all traveling at the same linear speed measured in meters per second? And you say, well, no. And you know that because if you're holding hands or whatever and you're going, we call it the whip, when we used to skate as kids, the one on the outside is going to be going by far the fastest of all of them. And in fact, the guy in the middle is not moving at all. He's just digging his skates in and pulling everybody around. So how does this speed depend on the distance from the center? And as it turns out, it's directly proportional to the distance from the center of the circle. And the proportionality relationship is this one, that speed is equal to the radius times the angular speed, omega. And that gives you the tangential speed, so-called, in meters per second. And all this is saying to you is that the further out you get from the center of the circle, the faster you're going to be going, just like these skaters, the skaters near the outside. So that's the physics. The tangential acceleration is how much this guy here is accelerating. So suppose all of these guys in a line are skating, they start at rest down here and they're skating faster and faster as they go around. What this guy measures, the tangential acceleration measures, is how fast that speed, that tangential speed, is changing. We're not comparing how this guy's speed with this guy's speed, but we're asking, how does this guy's speed change with time? If he's increasing, if he's accelerating in this direction going around this arc, then he'll have a tangential acceleration. And that's given by r times alpha. So this is a relationship between a linear quantity measured in meters per second squared to an angular relationship, an angular acceleration measured in radians per second squared. And the constant of proportionality is the radius measured in meters. Let's look at this one also. This tangential speed is measured in meters per second. The radius is measured in meters. The angular velocity is measured in radians per second. So the units of this guy, r omega, are going to be units of meters for r, and units of radians per second for omega. And that gives us units of meters per second. And you say, what happens to the radians? And I say, poof, not really a unit. Disappeared. Same thing happens here. This is a tangential acceleration measured in meters per second squared. This is an r measured in meters. This is an alpha measured in radians per second squared. But meters times radians per second squared gives meters per second squared. The radians disappear. Just like magic. And then finally, the centripetal acceleration. This one's the simplest one to deal with because you've seen it before. And it's just going to give us a little bit more algebra. You remember A is v squared over r from chapter 5. And now we know that the tangential speed is equal to r omega. So I've put in r omega in for v tangential, and I'm going to square it. Well, that'll give me r squared omega squared over r. So that's what this gives me. This r kills one of these r's, and we get r omega squared. I wouldn't really memorize this. I would just remember this from chapter 5, a is v squared over r, and then remember this. And if you ever need to get this, you can substitute this, sorry, so many thises, into here. So that's the tangential speed, tangential acceleration, and centripetal acceleration. So the physical difference between the tangential acceleration is that it measures how fast this guy is. It measures changes in his angular speed. His tangential speed. How his speed is changing. He's going faster and faster and faster, skating faster around the corner. The centripetal acceleration. So this is a centripetal acceleration. This is tangential acceleration. The centripetal acceleration measures the acceleration simply due to the fact that that velocity vector direction is changing, like we talked about. This guy measures how the velocity magnitude is changing, and this guy measures how the velocity direction is changing. Let's do an example. A helicopter blade has an angular speed of 6.5 revolutions per second and an angular acceleration of 1.3 revolutions per second squared. For point 1 on the blade, here we are, find the tangential speed, the tangential acceleration, and the centripetal acceleration. Well, first of all, we're going to need the, what's this called? Omega is the angular velocity. We're going to need to get that in the right units. We've been given that the angular speed is 6.5 revolutions per second, but I can convert that to radians per second by saying that we have 2 pi radians in 1 revolution. That'll give us an answer in radians per second, 40.8. No big deal. Alpha is angular acceleration is 1.3 revolutions per second squared. So that's what we're given alpha in, but normally we like to measure alpha in radians per second squared. We can convert that in the same way. 2 pi radians per revolution, plug the numbers in, and you get alpha in the correct units, radians per second squared. Now, we can get all of these different quantities. Vt is r omega, r is 3 meters, omega is 40.8 radians per second, and that'll give us 123 meters per second. Had we not converted omega to radians per second, we would have gotten the wrong answer here. This equation, and this one also, actually all 3 of these equations are valid only if omega and alpha are measured in their correct units with radians. Radians per second for omega, radians per second squared for alpha. This just gives us the the results. 123 meters per second is how far that point is moving at this point here. Pretty good rate of speed for sure. This alpha says how fast this point is accelerating. It's going faster, 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 faster as it's moving around. That gives that linear acceleration of that point, tangential acceleration. And then finally, for the centripetal acceleration, it's huge. And that gives the inward pointing acceleration due to the fact that the velocity vector is changing direction. 2 points are located on a rigid wheel that is rotating with decreasing angular velocity about a fixed axis. So we've got a wheel. It's rotating with decreasing angular velocity. So let's say this is our initial situation, and this is our final. So, and I'm just denoting the final with, well, hopefully the same size circle here, but with angular velocity that's less. So I drew less of an arc here than I did for the initial angular velocity. Point A is located on the rim of the wheel, and point B is halfway between the rim and the axis. So here's point A on the rim. Point B is halfway between the rim and the axis. Which one of the following statements is true concerning this situation? Okay. So what we're imagining here is we've got a wheel that's spinning fast in a counterclockwise manner. That's positive direction, but it's getting slower and slower and slower. So what's true? Both points have the same centripetal acceleration. Well, the centripetal acceleration, as we worked out, is given by r omega squared. The r's are not the same for point A and point B. The radius for point A is twice that for point B. So the r's are different, but the angular velocity of both A and B is the same. That's when we first introduced the concept of an angular velocity, and I tried to emphasize to you that any point on that circle is going to rotate through the same angle in the same amount of time as any other point. So this is the same for both. The omega is the same for A and B, but this is different. And what this point A here is saying is that both points have the same centripetal acceleration. That can't possibly be true. Both points have the same instantaneous angular velocity. Well, what about that? This is the instantaneous angular velocity, and we just made an argument that that has to be the same. So this is, in fact, the answer. Both points have the same instantaneous angular velocity. Let's look at the other cases too, because they're instructive. Both points have the same tangential acceleration. Well, what about the tangential acceleration? That's r times alpha, according to that second equation near the bottom. And this is the tangential acceleration. That's supposed to be a t. Didn't come out very clearly. A sub t. Well, r is not the same, and alpha is the same for both. So this is going to be the same for A and B. If the instantaneous acceleration, if the instantaneous velocity, omega, is always the same for all different points on the particle, then the instantaneous acceleration, alpha, must also be the same for all points on the rigid body. So that's going to be the same for all the points. R is not the same. And so what that says is that this tangential acceleration cannot possibly be the same because R is different. Each second point A turns through a greater angle than point B. Well, let's ask that. Let's say in a second point B gets up to here and point A gets up to here. Does point A turn through a greater angle than point B? Is that angle any different from this angle? You say, well, I don't think so. It looks to me like both angles are pretty close to 45 degrees. And you'd be right. And in fact, it's the same argument that we went through before, that all points rotate through the same angle in the same amount of time. So that's not correct. And then finally, the angular velocity at point A is greater than that of point B. So the angular velocity is omega. Is that angular velocity at point A greater than that of point B? And you say, well, no, they're the same. And you're right. The angular velocity at point A is the same as the angular velocity at point B. Same holds true with the angular acceleration. Angular acceleration at point A always is the same as the angular acceleration at point B that's halfway in. So we talked in Chapter 5 about uniform circular motion. You got something that's traveling at a constant speed, which we're now calling the tangential speed. It's a constant speed, although the velocity direction is changing, the speed is constant. That's uniform circular motion that we talked about in Chapter 5. Now we're not in Kansas anymore, and we get to think about non-uniform circular motion, where you can have not only an centripetal acceleration toward the center of the circle, like we did in Chapter 5, but also a tangential component of acceleration in the direction of motion or opposite the direction of motion. And the total acceleration of that object, and so this would be in the case of the airplane speeding up. So you release the airplane from rest. Somebody's here holding the airplane. Releases the airplane from rest. It takes off. It's accelerating, and it's not a uniform circular motion. It's accelerating. That's reflected in this tangential acceleration. Let's do an actual example and calculate it. Starting from rest, an athlete accelerates a discus to a final angular velocity of 15 radians per second. So that is the final angular velocity, omega. In a time of 0.27 seconds, that's the elapsed time. During the acceleration, the discus moves in a circular arc of radius 0.8 meters. At the final time, find the magnitude of the total acceleration. All right, we're going to have two components of acceleration. A centripetal component pointing toward the center of the circle, and a tangential component that's around the rim of the circle. The centripetal component, as we showed a couple of slides ago, is going to be the radius times the angular velocity squared. And luckily, that's already given to us in radians per second. We can plug that in, and we get a centripetal acceleration of 182 meters per second squared. Pretty good sized centripetal acceleration. What about the tangential acceleration? That is r times alpha. Here's the r, comes along for the ride. And if we want to find the average angular acceleration, we can find that as the final angular velocity minus the initial angular velocity divided by the elapsed time. R is 0.810 meters, that's the radius. The final angular velocity is 15 radians per second. The initial angular velocity is 0, started from rest. And then the elapsed time is 0.27 seconds. And plug those numbers in and you get the tangential acceleration. And now to find the total acceleration, we have two components, a tangential component and a centripetal component. We can make a triangle. And this tangential component looks like that over here, but if I move it to the other end of that triangle, then I have a right triangle with two legs, AC and AT. And the total acceleration will be the hypotenuse. So we can just appeal to our Greek friend, Pythagoras, and take the square root of the sum of the squares to find the total acceleration. Now, what if we wanted to know the actual direction that that acceleration was in? That's also possible, and you use the same triangle. This angle phi here, we could we can say that the tangent of phi is AT over AC. The opposite side divided by the adjacent side. And then take the inverse tangent. We could plug the numbers in here for AT and AC. We calculated them right here. Plug those numbers in, take the inverse tangent to find the angle. I think there's a problem or two that asks that.